Okay, we're back. This is Stats260. We're looking at 8.2, Chapter 8. We're in Chapter 8. We're looking at 8.2. So, an example. A researcher reports, first of all, the formula for Z. We already know Z-score. To find a Z-score, remember that standard deviations above or below the normal, on a normal curve above the average. And so we take the sample average, x bar, minus the sample of the population, divided by the standard deviation of the population, divided by the square root of your sample size. Bigger sample size, better. And so we'll look at how we make conclusions statistically, all right? Lots of people are throwing a lot of data out there in the world, especially nowadays with the internet and everything else, that it doesn't stand up because they're making conclusions about things. And now sometimes there's an old saying, statistics don't lie, but liars use statistics. So you've got to be careful. You've got to see who gathered the data, why did they gather the data, what do they have to benefit from one presentation of the data being this way or that way. And a way that you can get through all of that is you can look after you find out who did it, because just who did it shouldn't necessarily invalidate the data. What should is what was the sample size? Where did they get these numbers? We're like, so for example, this first example, a researcher reports that the average salary of assistant professors is more than $42,000. A sample of 30 assistant professors has a mean salary of $43,260. At a 5% level, at 0.05, alpha is 0.05, so significance level of 5%, test the claim that the assistant professors earn more than $42,000 a year. The standard deviation of the population is 5,230. So we have to decide, is that statistically significant? We know that this number is bigger than that number. And so a lot of people just jump to that conclusion. They just say, oh, no, they earn more. Because look, we averaged 30 of them and they ended up, that much more. Well, you have to look at the variation in the data, because we're making a generalization about the population. Remember, when we're doing all of this, it's about the population. So if you say, well, is that more than that? It is. These 30 assistant professors that you found their salaries and added them up and divided by 30, that is bigger than what the national average 42,000 is. The question is it significant? Is it significant enough for us to say, oh, it's more than 42? Now, when we're done with this, we're still basing on that 42. We say it is 42 or it is greater than 42. We don't say, well, now the new one is this, 43,260. That's not true. The sample had that, not the generalization. So we're still focused on that. And then if it is true, then we take a look and say, well, maybe we should look deeper into this. How important is this? All right? So there is an A, B, C, D, E, a 5-step thing I want you to do on every one of these problems. I kind of designed this as I started teaching the class, and the book does it too, so I kind of ripped it off out of the book, but I put it on every problem so you get used to doing these same steps. So A is state the null and alternative hypothesis. And when we do the test on this, don't worry, I will set it up with an A, B, C, D, E. So all of them will have that on there for you. So we want the null hypothesis and we want the alternative hypothesis. All right? So here, the null hypothesis is the standard deviation of the population, mu, is equal to 42,000. And now this is where some interpretation comes in. You got to read it over. It says, test the claims they earn. That's really ugly even for me. Earn more. So we're testing the claim that the is greater than 42,000. Now, Notice, your null and your alternative hypothesis should have nothing to do with this. This is just a little piddly sample. It's only based on 30 people. That isn't enough for us to make generalizations about the population. All right? So that's always step one. Step two, draw yourself a pretty picture. So we're going to draw a standard normal curve, and we're going to mark it up. So we've got some information that they've given us on this. We know that alpha is 5%, and it's a one-tailed test on the top end, a right-handed one-tailed test. This is 5%. That means that this cutoff is 95%, 0.9500. So anything, if I end up finding this z-score and it puts me above the 95th percentile in here, then I reject the null and conclude that this is true. If it ends up in here, then I fail to reject the null and say, no, that wasn't high enough with this standard deviation and this sample size to make it statistically significant. It's not different. All right. So let's do part C. Part C is find the test statistic, which is find your z-score. So finally, some math. We put in the 43,260 minus the 42,000 over the 5,230 divided by the square root of 30. All right? And so when we work that out, it ends up being 1260 on top and 954.862 on the bottom. That is 1.319. So that gives me a z-score of 1.32. All right. So letter D is we decide reject the null or fail to reject the null. So D is decision, and E is conclusion. So before we do that, we have to go to our chart now. We have to look at our chart. We could do a couple of things with the chart. We could look up the z-score, the probability that goes with that, and put it on here. We know this cutoff is 95%. If we want to just use z's, then we would have to look at, let's look at that. Let's look at the critical value here, the CV cutoff. What is the z-score right there? What's the z-score that goes on a one-tailed test? So either way, we're going to use our chart. I'll show you 2 ways to use your chart on this problem. All right. So look at your chart. We've got our chart here. We want table F. So table F. And we want, look at on the side here. It says one-tailed theta. Oh, I don't know. Did that zoom in right? So one-tailed theta or two-tailed theta. Well, this is a one-tailed test, and we want 5%, and we get to use z. So we go all the way down to the bottom, and that is 1.645. So let's put that in. 1.645 is this. Critical value, 1.645. So basically, if this number is bigger than 1.645, it'll be there. If it is less than 1.645, it'll be, well, it's here. So that's where we ended up. Our test statistic ends up in the non-critical area. So that non-critical area, it's not in the little shaded area. That means anything in here is evidence for fail to reject. Anything in here is evidence for reject. And so since it ended up in the non-critical area, our decision is fail to reject the null. Okay, so we failed to reject the null at a 5% significance level. What does that mean? What's our conclusion then? Well, if we fail to reject this, we failed to reject the null and conclude that, that means this is our conclusion. We're concluding that the mean salary of assistant professors is $42,000. All right, so we failed to reject the null. What does our conclusion look like? We failed to reject the null. We failed to reject the null. Null at 5% significance level. And so we conclude the average salary for assistant professors is $42,000. And so what we're doing when we say we conclude, you just go back and look at, either we're going to write this out in words, the average salary is $42,000, or the average salary is greater than $42,000 if we would have rejected that and concluded that. So we conclude that assistant professors make an average of $42,000 per year. All right? So now what does that mean? If we ran this experiment many times, we would get results like this about what is 1.32. So look, we just kept it to z-scores here. The cutoff z-score was 1.645 to bump it into the top 5%. And so we know it, based on this, we knew it was less than the 95th percentile. But how much less? Well, let's take a look. If we look at our chart for z-scores, we can look that up. So for the z-score, we can use 1.3, and then follow it over to 2. 0.9066. So 0.9066. 0.9066. What does that mean? That means it's about the 91st percentile is where it's scored. So because we set this at 5%, now what you shouldn't do, but people do, is they'll play around with that alpha. All of a sudden that alpha, if that alpha would have been 10%, this would have been significant. At the 10% level, we would have rejected the null and concluded that assistant professors make more than 42,000. And so if there's a weird alpha setting on the data, if you're looking at a workup of a statistical analysis, and they've got some kind of wonky 12% significance level or 13, 14, something, usually 5, 10, 15, and 20, I've seen those, all right? But if it's weird, if it's 8%, if it's 8.7% or something like that, that means they did it, they didn't like the results, and they went back and changed it. They went back and changed their alpha setting. And you really shouldn't do that, especially when to make it weaker. To make it stronger, that's fine. I've seen that happen already, where they've set the alpha at 5%, but it became so small, they moved it to 1%. That's fine. You can always make it smaller, as long as it doesn't change the results of your study. If you make it larger to change your results of the study, that's a little questionable. That's kind of, that's where the saying, statistics don't lie, but liars use statistics comes from. So what this means, what does 91% mean? I'm not going to write that down. I'll just state it in words. That means if we did this experiment many, many, many more times, we would get results like this 91% of the time. And so that's not a significant amount because we set our significance level at 5%. All right, so 91 doesn't count as, the 91% doesn't count as significant. All right? Okay, so let's look at a couple more. One more problem, and then we'll talk about, p-values. I just really talked a lot about p-values already. So let's look at the next problem. 42. So we're on to page 4. And it's a national magazine claims that average college student watches less television than the general public. The national average is 29.4. So this is an old study because we all watch lots of different screens now, not just TV. With a standard deviation of 2 hours, a sample of 30 college students has a mean of 27 hours. Is there enough evidence to support the claim, at a 1% significance level? So, I don't know. Let's see. So, this is letter B. It's a second example. I'm not going to put that down, though. Let's go A. State the hypothesis. B. Draw a curve. C, run the test statistic. And then D and E is reject or fail to reject. And E is do the write-up. All right. Okay, so first, let's state the hypothesis. Well, the null hypothesis is equals 29.4 hours of TV watching. The alternative hypothesis, they think that college students watch less than that. So less than 29.4. Notice, it's always based on the population. We don't, that 27 comes into play when we calculate our test statistic into this equation, but it does not make the hypothesis. It's small potatoes. All right? Draw the curve. So here's our standard normal curve. It's less than, and again, we had to read that out of we had to pull that out of there. If they say not equal to, we put a not equal to, it'd be a two-tailed test. If it's greater than or less than, you got to read that carefully. So the national average is, all right, a sample of 30. A national magazine claims the average college student watches less television. So you've got to reread that part carefully. That's the biggest stumbling block for that one. Okay, so less than is going to put it as a one-tailed test on the bottom end. And the significance level is 1%. So that's 1% for our critical area. All right. Okay, so, and we can look that up. Let's see. C. Yeah, let's find our critical value here. Let's find our CV. Our CV is going to be a z-score. But what is the z-score for 1%? And it's below the mean, so we're going to have to make it negative. So if we have one tail, take a look, one tail. and then we go to 1%, all the way to there, and then down to the bottom. It is 2.326. So we're going to call our critical value, the z-score for the critical value, is negative 2.326. All right. All right, let's find our test statistic, Z. The suspense is killing me. Not really, I've got my work on my paper. So let's see. We've got 29, we got 27 minus 29.4 divided by 2 divided by the square root of 30. All right. So when you work that out, work out the top, work out the bottom, do the numerator, do the denominator. If you're going to try to put it in your calculator all at once, you got to do parentheses around that and parentheses around that. I think it's easier to actually do a step of work here. Negative 2.4 divided by 0.3651. We end up with negative 6.572. Holy Toledo. That is definitely less than that. So that's going to be way into the critical values, right? So Z is equal to negative 6.57. That's 6 standard deviations below the mean, 6.5 standard deviations below the mean. We only needed it to be 2.3 standard deviations below the mean. So it's way smaller. So yes, definitely in the reject region. So that brings us to, should we reject or fail to reject? Well, that is definitely a reject, which means that this is our conclusion. Very much so. All right. And so we conclude that, so we reject the null and conclude the alternative. So what does that look like in words? Our conclusion is we reject the null hypothesis at a 1% level. All right, and we conclude that an average college student watches less than 29.4 hours of TV in a week. Less than. So we're basically restating this hypothesis. Mu is less than 29.4. So the college student watches less than 29.4 hours of TV per week. We've got to be careful on this, and the reason that I'm talking like that is because so many students over my career have done this. They'd say, so we conclude they watch 27 hours. No, that's not what we were testing. That was data that we used to figure out the answer to this hypothesis. But the hypothesis, that's why it's the first step. You set that up first, and your conclusion is always either going to be this or this. It's not going to have that in there. 27 won't be in there. That's just a sample, all right? If we ran this experiment many times, we would get results like this less than 0.01% of the time. If you look at your chart for z-scores, when it goes that low, there's a little addendum on the way bottom in really tiny little letters. It says for Z, so on table E, the z-score chart, for Z values less than negative 3.49, use 0.0001. And so if we were doing a p-value, this was 1%. Well, our work turned out to be less than 0.01%. And so it is definitely significant at the 1% level. All right. And then the last one, number 3, is not a problem. It's just, it says p-value. The p-value is the actual area under the standard normal distribution curve, representing the probability of a particular sample mean or a more extreme sample mean occurring if the null hypothesis were true. So if the null were true, we would get results like this less than 0.01% of the time. So that's why we don't think the null is true. It would be very unlikely that that would be true. So if we had the p-value right up on this, that's 0.0001, because it's off the charts small. That's 0.01%. If the null were true, we would get results like this 0.01% of the time. So if the null were true, we would get results like this 0.01% of the time. Now, if you look at the notes, therefore, we reject the null and conclude college students watch less than 29.4 hours of TV a week. We already stated that right there. But if you look at the notes carefully, it says, now look, I put 0.01% and then I make my students write after that less than 1%. Because when it's really small percent like that, a lot of people in the general public, when they see that, they still just see 1%. They don't see 1/100th of a percent. If you want to stress it that it's less than 1, you can put it as a fraction, 1/100, so 1/100th of a percent. That's really unlikely that that the null is true then. So the conclusion is always based on the null. So if the null were true, we'd get results like this, less than 1% of the time. All right. Okay, the next video will be on 8.3.